Okay, so let's take a look at 8.2, our last kind of more difficult unit here. So last time we were talking about rational expressions. We looked at our parent graph of y equals 1 over x. We compared horizontal and vertical asymptotes. Now we're going to look at a little more complicated ones. Before we do that, let's kind of backtrack. So if I want to talk about a continuous function, continuous at its heart really just means that the graph flows from one point to the next nice and neat. There's no gaps or anything. So all of our polynomials that we've done throughout all this are continuous. It can go back and forth. As long as you can draw the graph without picking up your pencil, essentially it's continuous. What we're going to be looking at today are discontinuous graphs. And when we talk about discontinuous graphs, there's a couple different ways it can be discontinuous. So we could have a jump where the graph comes up to a single point and then magically reappears somewhere else. So that's a discontinuity. You can have a hole where the graph looks perfectly normal, except it just doesn't exist in a single spot. We can have our asymptotes that we've done, where it goes up, or it could even be an asymptote where they both go in the same direction. So all of these are discontinuities. These are points on a graph where it is not continuous. In particular, we're usually going to be interested in the x values. So all of those x values are called discontinuities. They're points where the graph does not function normally. It's no longer continuous. There's either a jump or a hole or an asymptote or something is wrong. So we're going to be looking at discontinuities as our main focus today. Now, of these, we need to make a decision: is something removable or not? Basically, a discontinuity is removable if you could put a single point, if we could just drop a single dot somewhere and fix it. Well, there's nowhere we could put a single dot here. That would still be a big gap, so it's no good. We could actually fill in the little hole with a single dot, which means that holes are removable. Asymptotes, nah, that's completely broken. Asymptotes, that's completely broken. So in point of fact, the only one that we can actually remove is a small hole in a graph. That is going to be a removable discontinuity, so holes. Not removable for the sake of what we're doing today is usually going to mean it's going to be an asymptote. We're not going to be dealing a whole lot with jumps. We're not going to be dealing with piecewise functions so much, as we're going to be looking at either holes or asymptotes. So let's kind of take a look and trying to put this together. So if we're dealing with a generic rational function here, what we're really going to look at, to make it a little bit simpler, is that we're looking at polynomials. So we're going to have a polynomial of some kind on top, and we're going to have a polynomial of some kind on the bottom. As an example, we could have something like this. We could have x squared plus 3x plus 2 over x squared plus 7x plus 12. So this is a rational function. We have a polynomial on top, we have a polynomial on the bottom. When we go to analyze these, we want to tend to look at it in specific order. So first things first is we need to know where's the graph breaking. And the graph is going to be breaking. The graph is going to be chopped up based on when the denominator is equal to 0. So our discontinuities are going to occur when the denominator, our x squared plus 7x plus 12, is equal to 0. So we're looking at when q of x equals 0. For the most part, that's going to be when we can factor it. Otherwise, we'll have to use the quadratic formula or anything else that's appropriate to do. So in this case, this guy is x plus 3 times x plus 4. So we'd get x plus 3 equals 0, or we get x plus 4 equals 0. This gives us two different discontinuities, x equals -3, x equals -4. So those are going to be the points where something went wrong with our graph. We haven't talked about are they removable or not yet. We'll get to that in a little bit, but these are the points where something went wrong. Now, to know if it's removable or not, we need to go look at the top. So I'm going to factor the top now, and we're going to compare the equation as we go. So if I factor the top, that's x plus 2 times x plus 1. On the bottom, we have x plus 4 times x plus 3. Something is removable only if its corresponding factor got canceled. So x plus 4 can't cancel, x plus 3 can't cancel, so both of these would be non-removable. They would both be asymptotes. So this is also non-removable. This is an asymptote. If it was able to cancel, we'd be able to say that it is actually a removable, it's a whole. Well, what are some other interesting things we need to know? We need to know when the graph is equal to 0. So if I take a simplified form of the graph here, after we cancel anything else, then I can take the top and I can set it equal to 0. That will actually give me my zeros, or my x-intercepts. Remember, they effectively mean the same thing. So I can take my top there, x plus 2 times x plus 1 equals 0. I get x equals -2, x equals -1. Those are going to be my two zeros, or x-intercepts. All right, so we can get couple more pieces of information out of this, and then we're going to do some background information on how to deal with range, because range is actually kind of the weird one for these. So let's see, we've figured out the discontinuities. And hey, if we know where the graph is broken, then we can actually answer what the domain is like. Because the domain for polynomials is going to be all real numbers, but it can't be where the graph is broken. So in this case, it's all real numbers except x cannot be equal to -4 and x cannot be equal to -3. So again, our domain is all real numbers, but we can't use those broken spots on the graph. We can't use our discontinuities. We figured out our x-intercepts. How about y-intercepts? Well, y-intercepts, nothing's changed from way back when. We're just going to plug in x equals 0 right into our original function. If I plug in a 0 right here, on top we'd have 0 plus 0 plus 2. On the bottom we'd have 0 plus 0 plus 12. So my y-intercept would be 1/6. So that hasn't changed. All right, so if we look at all the information we've gotten already, we've already gotten what the discontinuities are. We've identified if they're asymptotes or wholes. We figured out the domain. We figured out the zeros, or the x-intercepts. And we figured out the y-intercepts. The hard part is going to be range. So let's kind of look at one big example. We're going to stop partway through it and talk about how to find range. So let's take a look at another one. So how about we were dealing with x squared plus 3x plus 2 over x squared plus 6x plus 5. So when I go to analyze these, the very first thing I'm always going to do is I'm going to factor and simplify. So that is step 1 in our process. So let's factor and simplify this. So if we factor it, on top I'd have x plus 2 times x plus 1. On the bottom I'd have x plus 5 times x plus 1. So x plus 1 would actually kind of cancel out, and we could simplify this to x plus 2 over x plus 5. Okay, so that's my first step when I look at these problems. I factor and I simplify. The second step is I'm going to find the points of discontinuity. So I'm going to find the discontinuities and identify them. So let's find them first. So again, to find our discontinuities, we're going to take the bottom of the fraction and set it equal to 0. So that was our x squared plus 6x plus 5 equals 0. So we can factor it. That's our x plus 5, x plus 1 equals 0. So we'd get x equals -5, x equals -1. There are my two discontinuities. Now I'm going to ID the discontinuities. So are they removable or not? So to tell if it's removable, we go see, would its factor cancel out? The x plus 5 does not cancel, so this is non-removable. It is an asymptote. If we look at x equals -1, the factor that gave us that would cancel out. So this is removable. Means for our graph that it is actually a hole in the graph. Okay, so we found the discontinuities, we identified them. Now let's talk about the domain. Once we've done the discontinuities, domain is easy. My domain is going to be all real numbers, but it can't be those discontinuities. So it cannot be x equals -5 or -1. Okay, let's look at our x-intercept. X-intercept. Well, I'm going to take a look at my simplified form here, and I'm going to set the top equal to 0. So x plus 2 equals 0. So my x-intercept is x equals -2. Be careful not to set the original equal to 0. You'll get -2 as one answer, but you'd also get -1 as another 0, and that's simply not true. -1 is one of our discontinuities. There is no y value there. It doesn't exist. So when we go to find the x-intercept, we want to deal with the simplified format. So we have one x-intercept. Y-intercept. All right, so our y-intercept, we're going to plug 0 into the original function. So if x equals 0, my y would be equal to 0 plus 0 plus 2 over 0 plus 0 plus 5 is 2/5. So there's my y-intercept. So all these are pretty straightforward. Now we got to figure out something new that's a little bit harder. And that is, how do we find the range? It's not as simple as range has been before. So we have a couple problems with range. So let's kind of sidebar this. We'll come back to this same problem. And let's talk about range. So I know range has got to be the y values, right? It's all the y values that can show up. So last time we had problems with range when we had horizontal asymptotes. So when we have a horizontal asymptote, like when we did y equals 1 over x, for an example, we had a graph that looked something like this, and it never actually came down to the bottom. Over here, it would do something like this. And again, it never makes it up to that top. So here's our problem, is that we had a horizontal asymptote of y equals 0 in this case. It just didn't work. So that has to be part of our range. We need to know, is there a horizontal asymptote or not? Our second problem is we just got done talking about discontinuity. So what if we have a graph that does stuff and then there's a hole in it? That means that that hole, that y value might not exist either. So we also need to figure out, is there a hole? What is the missing y value? So that's what we have to look at to deal with our range. So let's talk first about the horizontal asymptotes. This is going to be a really helpful portion for your notes. Make sure you star this. I'm going to give you basic rules for how to tell horizontal asymptotes. Okay, so our whole goal here is we're dealing with some kind of rational expression. We have a function on top, we have a function on bottom. What we need to look at is we need to look at the degree of each of them. That's really what we care about. The degree of those polynomials is going to tell us what happens. So let's say the degree on top is m, the degree on the bottom is n. So our first case here is, what if it's bigger on top than on bottom? So this could be an example of like x cubed plus 1 over x plus 5. So the degree 3 over degree 1, the degree on top is bigger. If the degree on top is bigger, then there is no horizontal asymptote. All right, so our second possibility, if we're comparing two numbers, is that the one on top is smaller. So this could be something like x squared plus 2 over x to the fourth plus 1. So degree 2 compared to degree 4, the one on the bottom is bigger, so the one on top is smaller. If this is their case, our horizontal asymptote is y equals 0. Our final possibility is that they are the same. So same degree on top, same degree on bottom. So let's say we have 2x plus 5 over 5x plus 1. So both of these guys are degree 1. They're the same. What we are going to do is we're going to do the lead coefficient of the top over the lead coefficient of the bottom. So my lead coefficient of top would be 2. My lead coefficient of the bottom would be 5. So we'd have a horizontal asymptote of y equals 2/5. So these are our three possibilities for horizontal asymptotes. The degree on top is bigger than the bottom, which gives us none. The degree on the bottom is bigger, or the degree on the bottom is bigger than the one on top. That gives us y equals 0. Or they could be the same degree, in which case we use the ratio. Okay, so we have that information. So let's go back to that problem we were working on. So we were working on this, our x squared plus 3x plus 2 over x squared plus 6x plus 5. So we have two things to check for range. Our first is horizontal asymptote. Okay, so we check the degree on top is a 2, degree on the bottom is a 2. They're the same degree, so we're going to look at the coefficients. Lead coefficient is 1 over 1. So we have y equals 1 over 1, so horizontal asymptote of y equals 1. So that means y equals 1 cannot be part of our range. It is our horizontal asymptote. Our next step is to check the hole. Okay, so is there a hole? This problem did have a hole. It had a hole at x equals -1. So to find our missing y value, I'm going to take y equals our simplified version here, our x plus 2 over x plus 5. And I'm going to plug in the missing x value. So we know there's a hole at -1, but we've canceled that out as we simplified. So I'm going to plug x equals -1 into our simplified equation here in order to find out what that hole's y value should have been. So if I plug in x equals -1, that'd give me -1 plus 2 over -1 plus 4, sorry, 5, which gives me 1 over 4. This is the missing y value that should be part of that hole. So when I go to talk about the range, our range is going to be all real numbers. It can be anything it wants. But we have a horizontal asymptote of y equals 1. And there's a hole at this specific point. So you can be a little bit lazy, so we can say our range is typically going to be all real numbers, except y cannot be equal to 1 from our horizontal asymptote. And we need to mention that hole. So in particular, we also does not include, so you could write does not include the point -1, 1/4. For the sake of this course, if you just want to tell me that the 1/4 was also excluded at that point, I'm not going to penalize you. It is possible that 1/4 exists somewhere else for the graph, so it's technically not completely omitted from the range, just that that particular y value at that point is gone. So now we've kind of covered everything. We've talked about how to find the discontinuities and identify them. We talked about domain, x-intercept, y-intercept, and range. So let's put it all together and do a problem start to finish with it. So let's take a look at y equals x plus 3 over x squared minus 4x plus 3. And I'm going to run through that whole process start to finish. So first steps first, we factor. It gives us x plus 3 over x minus 3, x minus 1. That does not simplify, so we can't do anything else. Okay, so now I go to the discontinuities. So for my discontinuities, I have the bottom setting equal to 0. and I get x equals 3 and x equals 1 are my two discontinuities. Neither of those terms canceled, so they are non-removable. They are asymptotes. Okay, so we have identified the discontinuities and told what type they are. Now I can move on to my domain. My domain is going to be all real numbers, excepting x cannot be equal to 1 or 3, because those are the two discontinuity points. Now I go to my x-intercepts. To get my x-intercepts, I go to the simplified form at the top. That's x plus 3 equals 0, and I solve it. So x equals -3 is my x-intercept. To get my y-intercept, I plug in 0 into the original function, so x equals 0. That would give me 0 plus 3 is 3 on top. 0 minus 0 plus 3 is 3 on the bottom. And I'd get y equals 1 is my y-intercept. If you want to write it as coordinate points, that'd be -3, 0, and 0, 1 are my intercepts. Okay, so that's the discontinuities and the type, the domain, the x-intercept, the y-intercept, and let's talk about range. So when we're talking about the range, we're looking for two things, horizontal asymptotes and holes. So I deal with my horizontal asymptote first. Top on bottom is a 2, top on the bottom is a 1. The bottom is bigger than the top, so we have a horizontal asymptote of y equals 0. Are there any holes? Okay, in this case, both of these were asymptotes. There's no holes to mess with stuff. So my range is all real numbers, but y cannot be equal to 0. All right, so that was it. These aren't necessarily hard. It's just a bunch of little steps as you go through and do them. So I'm going to do one more, start to finish, and then we'll talk about our last little topic. All right, so let's talk about x squared minus 3x minus 4 over x minus 4. Same thing, we're trying to find all those characteristics. Again, I start out, I factor it. So this is x minus 3. Oops, nope. See, this is why you have to be careful. This is x minus 4, x plus 1 over x minus 4, which means those would cancel, and this whole thing would just reduce to x plus 1. Okay, so discontinuities. We're going to take the denominator and set it equal to 0. So my denominator is x minus 4, so I get x equals 4 is my discontinuity. I go, I check, it could be the term that gave me x equals 4 canceled, so this is a hole. It is removable. Now I can talk about my domain. So my domain is all real numbers, except it can't be the whole, so x cannot be equal to 4. Okay, we can go to our x-intercept. X-intercept, I'm going to take the top of what's left, our simplified form, and set it equal to 0. So x plus 1 equals 0. We have one x-intercept at x equals -1. Y-intercept, I plug in x equals 0 into the original function. So that gives me 0 minus 4 over 0 minus 4. And it looks like we have a y-intercept of 1 again. Okay, so we did our discontinuities, identified them, our domain, x-intercept, y-intercept. Final part is range. So for range, we check horizontal asymptote, we check for a hole. So horizontal asymptote, the top is bigger than the bottom. None, no horizontal asymptote. We're good. Our hole. Okay, we did have a hole, it got removed. We know we have a hole at x equals negative, or x equals 4. So to find the y value, I'm going to plug that 4 into the simplified format. So y equals x plus 1, so that would give me 4 plus 1. Y equals 5 is our missing value. So my range is all real numbers, excepting it cannot be equal to 5 in this case. You could also write y does not exist at that given point, so you could have put it that 4 or 5 is not included as part of the range for the y value. However you want to phrase it, I'm being pretty forgiving with these because it's pretty weird. All right, so that's your process for most of the homework. We have one last topic to do, and then we are done here. So let's kind of go backwards. What if we needed to come up with a function where we know that it has certain characteristics? So if we had a vertical asymptote at 1 and another vertical asymptote at x equals 5, what if we have a horizontal asymptote of y equals 3/2? And maybe we know that the graph has some zeros. We know the graph has zeros at 2 and 6. So we're going to try to go backwards. We have all these characteristics. We just talked about how to find them. But how can we reverse engineer it? So we know these are rational expressions. So I know we're going to deal with some kind of fraction. I know vertical asymptotes came from us factoring the bottom of the equation and saying it equal to 0. So if I have a vertical asymptote at x equals 1, that means x minus 1 had to be one of the factors on the bottom. If I have a vertical asymptote at x equals 5, that means x minus 5 had to be one of those same factors. So having denominator of x minus 1, x minus 5, and them not canceling gives me vertical asymptotes. If it was a whole, I would have to have it be cancelable by the time we're done. Okay, zeros I know we got by setting the simplified version equal to 0 on top. So that means if there's a 0 at 2, we'd need an x minus 2. If there's a 6, it means we'd need x minus 6. Okay, so this is giving me vertical asymptotes at 5 and 1, so check. This is giving me zeros at 2 and 6, check. Now we look at a horizontal asymptote. This is where things will get a little bit weirder and why there's not necessarily one right answer for a lot of these problems. So for a horizontal asymptote of y equals a number, that only occurs when the degree on top compared to the degree on the bottom were the same. So this expression would give us a degree of 2, they're the same. Then our lead coefficient would have to be 3/2. So we need a 3/2. This meets all of the requirements. So let's try another one. How about we have vertical asymptotes at x equals 0 and x equals 6? How about we have no horizontal asymptote? And let's say we know that there is a 0 at least at -4. So I'm going to start the same way. I know that this is some kind of expression. We have a vertical asymptote at x equals 0, so x would have been a factor. We have a vertical asymptote at x equals 6, so x minus 6 would have been a factor. We have a 0 at x is -4, so x plus 4 would have been a factor. Okay, so we meet the requirement for that and that. But now we have a problem. It says at the horizontal asymptote, there isn't any. And that occurred when the top was bigger than the bottom. But on top, we have 1. On bottom, we have a degree of 2. So that's no good. So we have to somehow add things to this to make it so it'll become true. So we need to add other terms on top that will make this true. But we have to be careful not to change these as vertical asymptotes. If I just wrote x squared up here, yes, it would actually have no horizontal asymptote, but these x's would cancel, making this a whole and not a vertical asymptote. So instead, what I need something that's not quite the same. So if I put an x squared plus 1 up here, that's not going to change these asymptotes. It's not even giving us extra zeros in this case, since these would be complex. But it is raising the whole top up to a 3. If I don't like the x squared, I could have done something different. I maybe like the number 7. I could do that, and that would work. Or maybe I just want to be lazy and just square the top. Well, that'd take us even, but we need it bigger, so how about I cube the top? So there's a lot of different ways you can do this. So just kind of experiment and try it out and see what you can do with it.